first we must understand how our temperature profiles in evaporators work. So let's start with the vapor chest temperature. This is what we call the TV. So let's have here TV, T sub V, T sub V is our vapor chest temperature. And this vapor chest temperature is apparently the temperature wherein our vapor chest works. Now, vapor chest temperature is the temperature at which our evaporators work, and basically instead of using vapor chest temperature, our problems specify this operating pressure. So sometimes you would see the evaporator works at the pressure of something like this. So that's basically the operating pressure, and if you would be taking the temperature at that pressure, then you will be able to obtain the value of our vapor chest temperature. And typically this is the lowest temperature when we consider the temperatures that are and the profile of our evaporators. Now the next one, which is higher, would be the boiling point rise. Basically this boiling point rise is dependent on the compound itself and the concentration. So as this concentration increases, basically the boiling point rise increases. And then if you would add this temperature of the vapor chest and then the boiling point rise, you will be able to get the final or the solution temperature. So I would also like to emphasize that imagine your solution starting with the vapor chest temperature being that's the original boiling temperature of that solution. And because it has some ionic compounds, it will increase its boiling temperature. That's why the final liquor solution or liquor temperature would be that's the solution temperature, that's TL. So therefore, in this case, if BPR is not equal to 0, we know that T sub L is greater than T sub V. And then finally, the highest among all temperature would be the temperature of the steam. So to give you an idea, if BPR is equal to 0, we know basically that's T sub L is equal to T sub V. That's what we assumed before when we were computing. But BPR is not actually 0 when it comes to compounds that are quite, ionic. So we have T sub S, T sub L, BPR, and then TV. And right here below this vapor chest temperature, we also have something like the temperature of the feed because, the feed temperature would always be considered as well. But, this feed temperature is quite very low compared to these temperatures at the vapor chest. So that's it for our temperature profile. So I hope you've understood quite well. And then if you have a question like this, so what is the boiling point rise of a 30% sodium hydroxide if the solution is boiling at 200 degrees Fahrenheit? So this solution boiling at 200 degrees Fahrenheit is typically the T sub L. So that's where the solution is boiling already. So that's 100 degrees Fahrenheit. So if you would be able to take the boiling point rise and then subtract that from the solution temperature, then you will be able to get the vapor chest temperature in this case. But we're just determining the boiling point rise, so you don't have to bother for this vapor chest temperature. Okay, so to solve for this, let's take a look at figure 11 at your Paris handbook. It's on the section of evaporators. So just browse over that after this vapor liquid separation and some discussions about this utilization of temperature difference. So you would be able to get to this figure, and this is what we call the boiling point rise of aqueous solutions figure. Okay, how do we use this in calculating evaporation with boiling point rise? Now let's review this figure first, okay, just to give you the parts quickly. Now, as you can read from here, we have solution temperature. So this solution temperature is typically your TL or T sub L. So this is your T sub L. This is your T sub L, okay? And then this one is your boiling point rise. So it's like if you take the boiling point rise and then this solution temperature, then you'll be able to get your answer. Now, there's an arrow that represents something like this, and then it goes to that point. So that's actually the procedure that you can do to find the boiling point rise, but I'll be doing that from our question right here. So we're looking for the 30% sodium hydroxide boiling at 200 degrees Fahrenheit. So the first step is you look at the solution temperature, so that's at the rightmost side of this figure. So that's the solution temperature, and in this case we have 200 degrees Fahrenheit. So this is the 200 degrees Fahrenheit. You start with that. So you take a note at this point. So that's 200 degrees Fahrenheit, and it says here that it is boiling at, at 200 degrees Fahrenheit, you would be taking this 30% sodium hydroxide. So now that we have marked this 200 degrees Fahrenheit as the solution temperature, check naman natin yung ating concentration ng sodium hydroxide, and that is 30%. So you go back to this figure. So this is your sodium hydroxide. Okay, so the first thing that you have to do is to intersect that point from 200 degrees Fahrenheit going to sodium hydroxide. So that is step 1. Just disregard the weight percent of sodium hydroxide first. Just connect this 200 to your component. So in this case, that's sodium hydroxide. So I'll have 200 here. Kukonek ko siya doon sa sodium hydroxide natin. Okay? And take note kung saan ka mag-e-end dito sa pinakadulong portion natin. So right here is yung intersection natin dito sa line na to. Okay? So after doing that, you go back to the problem and take a look at your concentration, and that's 30%. So that's 30%, meron ka ng 200, meron ka ng sodium hydroxide, then the last arrow that you will draw will be going from the leftmost side dito sa pinakadulo nito, and then 30%. You would intersect 30%. So this is your 30%, and then dediretso tayo doon sa pinakadulo niya. Okay? So in that way, you can now obtain your boiling point rise, and that is simply equal to this one is 20, so around 25 or 24. So in this case, we could say that BPR is actually equal to 25 degrees Fahrenheit. Okay? So, you might be wondering, paano naman natin babasahin itong solution temperature? So, you disregard this values na kapag nanggaling ka dyan. Okay? So, di ba nanggaling tayo dito sa left side, which is, tinutukoy dito is your solution temperature, so that's 200. You intersect the component with this line, so that's sodium hydroxide, and then intersect mo siya hanggang doon sa dulo ng ating figure, and then lalabas ka ulit. Babalik ka naman by intersecting yung ating percentage, which is 30. And then kailangan mo siyang extend hanggang dulo para makita mo kung ano ba yung ating boiling point rise. So that's around 25 degrees Fahrenheit. So the answer is 25 degrees Fahrenheit. So in this case, we could say that T from, let's say, from figure 11 ano ba yun? 11-124. So 11-124, the BPR is equal to 24 degrees Fahrenheit. Okay? So, ganun lang siya kasimple. Okay? So, don't forget that, and huwag kayong malilito, kailangan nyo siyang idiretso kasi what if hindi natin siya diretso? Ginawa natin is hanggang dito lang siya sa sodium hydroxide lang. So, what if ganyan? And then we try to gawin natin is ganito siya. Diba? So, basically, mag-iiba na yung ating sagot. Magiging something like mas mababa siya. Parang around 20 or wala pa siyang 25. Actually, 24 dapat yung sagot. But 25 nilagay ko doon. 24 lang to. Kasi nga, mas mababa yung kanina. Okay? So, ayun, kung mapansin nyo. So, ganun lang siya ginagamit. Yung ating boiling point rise. So, kailangan lang dito medyo magaling tumingin. Okay? Pero, what if we try to solve for another problem using this concept? Now, this problem naman asks us about what is the boiling point of the solution at 50% KCl at 80.568 kilopascal. So, we know very well that this is looking for our T sub L because that's the boiling point of the solution. Remember, sinabi ko before na if you have a vapor chest temperature and then you add the BPR, you'll be able to get your TL. And then sabi dito, meron tayong 50% KCl and then 80.568 kilopascal. So we know na kung ito is 80.568 kilopascal, ina-assume lagi natin ito. So we have 50% KCl at 80.568 kilopascal. So basically, kapag meron tayong pressure na given, it is common na i-assume natin na this is the operating pressure. So in this case, our operating pressure would be that it is equal to 80.568 kilopascal. And knowing naman na yun yung ating operating pressure, we can obtain our vapor chest temperature from this pressure. So, from your Paris handbook again, you go back to that and then evaluate the 80.568 kilopascal from the thermodynamic properties of your Paris handbook. So, that is equal to, from Paris handbook, this is equal to 366.4832, and that is in terms of Kelvin. Okay, so we go back to figure 11 dash 124, I think. So we have here, actually sa simulang discussion lang siya ng evaporators, some 5-7 pages. Sorry, makita nyo na siya. Anyway, so yun nga, this problem asks us about T sub L. So iba naman yung hinahanap dito because in the first place, dun sa ating first solution, we were able to find BPR from our T sub L. Pero ngayon, T sub L lang hinahanap natin and we're given with this concentration as well as this vapor chest pressure. Now, would it be possible kaya para mahanap natin siya using that method as well? So, we know naman na this is the solution temperature, but wala tayong ganong value. So, I know you might be thinking na babaliktad natin yung procedure. So, ang gagawin natin is, baka sabihin nyo is, edi check na lang natin to and then ibalik natin siya, then yung ganon. I don't think, I hope na nagigets nyo yung point ko na iniisip nyo is babaliktarin kasi usually ganon yung iniisip ng mga students. Kasi 'di ba, usually ito kasi is from TL naging BPR, so technically may TV ka na. Pero the truth is, it is impossible to do that. Because the only way that you can solve for this is to do trial and error. Why is that so? Kasi kung mapapansin niyo dun sa ating solution kanina, 'di ba hindi naman natin siya in-extend natin siya, but we're just looking at the BPR and not the solution temperature. Hindi kasi na porket meron ka dito BPR and then yung katapat niya rito is yun na yung kanyang vapor chest temperature. So hindi siya nagwo-work that way. So the only way now we can solve for this is to assume. Okay? Mag-assume ngayon tayo ng starting natin na solution temperature. Okay? So, itong 366.4832, I would convert that in terms of degrees Fahrenheit. So, this TV is equal to 200 degrees Fahrenheit as well. So, yun pala. 200 degrees Fahrenheit din naman siya. So, we start with the same, yung ating TV is 200 degrees Fahrenheit. So, hindi ka dyan mag-i-start, yun yung ating ending. So, syempre, meron siyang boiling point rise. And we know very well na kung may boiling point rise siya, dapat mas mataas tayo sa 200. So, basically, nandito yung ating TV sa 200. So, ito yung ating baseline. Ito yung TV natin. So, let us assume na ang ating boiling point rise is 220. Boiling point of the solution is 220 degrees Fahrenheit. So, with that, 220, i-intersect ko siya ngayon sa KCL. So, that's 220, and then i-intersect ko siya ngayon sa KCL. So, hanapin natin ang KCL. So, siya ay, saan ba siya? Yun ang KCL natin. So, that is KCL. Okay? And then, so, yun na nga, na-intersect na natin siya. And then, after that, we go back to the same line, knowing naman na ang ating solution is 50%. So, you can try doing something like this. Okay, so 50. So, yun na yun. Okay, so you'll be able to get 25 as your BPR, around 24. Then, you can also try to... So, yan, mas okay na siguro siya. Medyo tataas pa siguro to ng konti. So, yan, parang medyo 26 nga siya, no? Kung mapansin nyo, diba, sa baba ko siya kinonek. Actually, pwede nyo rin siyang gawin sa taas and you will be able to get the same, same value din. So, diba, starting from this, you can also connect that with this expression. Kasi minsan kasi, pag sa baba, mas nakikita natin. Minsan kasi ito kasi is ginagamit pag matataas yung ating mga percent concentration. Kasi pag mababa, dito tayo sa baba mismo. Actually, hindi nakita dito kasi ito yung 50. So, hindi na pala siya kita dito, no? So, yung kanina, actually, pwede yon. Try natin, halimbawa, let's say, ano siya, 15% lang, ganon. So, kung 15 lang, di ba, pupunta siya dito sa point somewhere here. So, it's around gitna ng less than 5. Okay? So, medyo vague tong anong to kasi hindi natin ma-identify kung saan ba siya talaga mismo. Pero, kung dito natin siya ipa-plot kasi mababa yung ating concentration, ano ba sabi natin? 15. So, di ba, you can see right from here na hindi pala siya 5. Ano lang siya, parang mga 2.3, something like that. So, dito, mapapansin nyo, same lang yung answer natin, pero the thing is, mas madali dito kasi low yung concentration. So, itong portion na nasa taas is for lower concentration, ito ay for higher, pero same lang din sila, dapat ang magiging sagot. So, anyway, 50 yung atin. So, we go back to that. So, 50, and then, pag diniretso natin to, the boiling point rise, let's just use 30 degrees na, 25 na lang. So, assuming 220, ang boiling point rise ko, so, let's say we have T sub L, so, T sub L, so we have T sub L assumed, that is equal to 220 degrees Fahrenheit. And then BPR ko na actual na nakuha is based on this graph we have 25. Okay, 25 degrees Fahrenheit. So to check that we have TV that is 200 plus your BPR na actual which is 25 degrees Fahrenheit. So therefore meron kang 225 degrees Fahrenheit. So this 225 is not equal to 220. So, mali yung ating assume. Pero, magkakaroon tayo ng idea about that. Okay? Knowing na yung ating assumed is kind of, mas mababa siya dun sa ating nakuha, no? Kasi 220 to and then 225 yung ating nakuha. So, by that knowledge, pwede pa natin siyang itaas yung ating assumption. Okay? So, itataas natin assumption, pero hindi naman siya yung sobrang taas. Okay? So, gawin natin na ang i-assume natin ngayon is 225. Okay? So, kasi yun yung lumabas kanina. So, baka 225 din siya. Pero, syempre, hindi siya sakto doon, no? So, let's try 225. So, sana meet ko siya dito. Ito is 230. So, gitna siya niyan. Okay? Then, yung KCL is medyo malayo na dito. So, i-move natin to. Okay? So, yung line natin, makapunta na siya ngayon dito. Okay? And then 50% is somewhere here. Okay. So, we have something like this, and then okay, so based on our assumption, kung meron tayong 225, yung actual BPR na makukuha natin is around 20, I think that's 27, something like that. So, kung 27 yun, and meron tayo ditong 200, so we know very well na kapag in-evaluate natin siya, meron tayong 200 plus 200 base temperature natin, 200, and then dito 27, so that is 227. Ngayon, ating in-assume natin is 225. So, basically, mas mataas pa rin siya. So, let's try increasing pa yung ating solution. So, let's try doing 230. Okay? So, that's 230. So, sabi ko nga, as long as yung ating actual BPR na nakukuha is mas mataas pa, or yung solution dun sa ating inassume, then you can always increase that your assumption pa. So, ito, medyo bababa na siya ng konti. And then, though, konti lang talaga yung diferensya niya, no? So, ayun, and then 50. So, yung kung mapansin niyo yung 50, medyo itataas pa natin dyan. Okay? Oops, medyo napasobra. Okay? So, kapag meron tayong 230 assumption, kung mapansin niyo, meron tayong 28 something or 27 point something. So, with that knowledge, tinaasan natin, pero naglalay pa rin siya sa around 27. No? So, basically, the answer here should be around that value. So, let's make it 227 na lang. So, kung 227, medyo banda dito yan. Okay? And then, ito yung ating KCl. Mamumove lang tayo ng konti lang talaga. So, that's it. And then, yung ating, actually, yung dulo hanggang doon na rin eh. Actually, parang mamumove lang siya ng konting-konti. So, yun. And then, 50%, almost dun lang din. And then, yun nga, 227. So, basically, our BPR should be equal to 27 degrees Fahrenheit. Okay? So, di naman talaga siya sobrang hirap kasi kung mapapansin nyo, kung saan yung inyong actual na nakukuha, dun lumalapit yung inyong mga posibleng sagot. And then, by doing that, diba, nag-start tayo sa 220 ata, diba, dun 220 tayo nag-start. So, 220 nakakuha tayo ng around 225 ata yun. So, nung 225, increase siya sa 227. So, nung ginawa natin 230, naging ano pa rin siya, 28. Pero mas mababa na siya. So, ibig sabihin nun, kailangan pa nating mag-step down. So, kaya, tama siya na nasa 27 lang lagi yung ating magiging BPR. So, siguro kung mas exacto to, baka mga 27 point something pa to. Pero, yun nga, since dito sa ating graphical solution, medyo sakto na siya dun sa ating solving. So, yun lang yun. So, BPR is equal to 27. Actually, hindi pala yung tinatanong. So, BPR is 27 and then our boiling point of the solution is 227. So, therefore, your TL or T sub L is equal to 227 degrees Fahrenheit. That's obtained from 200 vapor chest plus BPR which is 27. Okay? So, yun lang yung ating paraan para makuha yung ating boiling point ng solution. Now, I would also like to discuss something from this book, handbook. Okay, dilitin ko muna kasi baka ma-save tong mga andito. Hindi tayo. Bawal yan sa board exam. I would also like to discuss something about this. We call this the Miranda and Furter na equation. And then, that's a correlation, no? Kasi itong figure dash 11124 is meron na nga siyang napakaraming uses. Pero if we have something like concentrated solutions of many inorganic salts, actually you can use this equation. BPR is equal to 104.9 n sub 2 raised to 1.14. Itong n sub 2 is the mole fraction of the salts in the solution. So for example, meron kang ang mole fraction ng mga salts na yun is 0.85. So you just use that mole fraction and then raise that to 1.14. So basically that will be your BPR. Okay? Kasi this is actually just a correlation. So in cases like that, kapag ka sobrang dami, kasi 'di ba? For example, itong figure, the figure na to is strictly for, let's say, isang compound lang. Pero what if ang dami niyang compound and then, or hindi mo alam yung compounds na yon, and then binigyan ka lang ng certain fraction na highly concentrated siya. So, basically, ito na yung gagamitin natin for such case na inorganic salt. Okay? Pero, yun nga, as much as possible, we'll be using that figure kasi yun yung talagang mas tama. Okay? Kasi knowing naman din na kung ano yung ating salt, 'di ba? Okay? So, let's try to check that dito sa atin What if we use this formula to find your concentration or BPR at this solution, 'di ba? So, let's say 30% sodium hydroxide. So, sabi dito, 'di ba, dun sa ating figure, we need to take the mole fraction of that in the solution. So, if you have something like 30% sodium hydroxide, we know that that's around 30 grams sodium hydroxide and then around 70 water, 30 grams sodium hydroxide. So if you take the mole fraction of this, so X and then NaOH, this is the mole fraction na mole. So this is equal to 0.1617. So if you will be substituting that in this expression, you would be able to get, so the BPR from that is 13.14115. That is based on this expression of Miranda and Furter. Okay, so we obtained this value, but remember this BPR is actually in degrees Celsius. So yun yung correlation niya. Actually hindi ata binanggit dito sa Paris handbook kung siya by anong unit, but it's in degrees Celsius. So yun. And then, if you would be converting that in terms of Fahrenheit, so you just have to multiply to 1.8. So, BPR from that solution is actually equal to 23.6541, and that's a fairly close value. Okay, so let's also check on KCl. So 50% KCl is something like x of KCl, and then we have this small fraction. So remember, tama siya kasi concentrated yung ating solution, but if it's not, then let's use the this figure now. So going back to this, so we have 50% KCl, so we have 50 grams, and then let's convert this to mole fraction. So that's 50 divided by molecular weight, and then 50 over 18. So KCl is around 45.55. I mean 74.55. So we have 74.55. That's per 1 mole. So we get 74.55 here. So we get x of KCl is equal to, so that's 0.1945. So I'll be using this to substitute it to the value of n sub 2 right here. So I'll be able to get 16.22. So I'll be able to obtain a value of the BPR, which is actually equal to 16.2225 degrees Celsius. And in terms of Fahrenheit, this is actually equal to 16.2225, and then you multiply that with 1.8 kasi diba, this is the change in temperature. So with that, you'll be able to get an answer that is equal to 004 degrees Fahrenheit. Okay, so that is a fairly close one to our solution as well in the figure. That's 27. Okay. So as you can see, it's quite accurate for concentrated solutions in organic salts at atmospheric boiling point. But of course, when the condition is not really that close to the atmospheric boiling point, then it somehow would deviate. Actually, you can look at here. The pressure is 80.568, and that's actually very close to the atmospheric pressure. So you would be expecting that your answer would be quite close with this BPR, but I'm allowing that to be used when your atmospheric pressure boiling point is used and the concentration is large. So we would say that the concentration is actually large when it's somehow equal to around 30 to and above, 30% and above. That's why this one is quite it has a a large concentration. And I would also like to emphasize that the concentration that is expressed in this manner is in terms of mole fraction. So those mole fraction that are expressed in, let's say for example, you converted that to mole fraction and then it's just around 0.18. That's actually large because the concentration in the mass fraction would give you something like 30 or 50%. So that's still large. It's a good example to be used in this expression. But for cases wherein the pressure is kind of very deviating from the atmospheric boiling point, then I would suggest that you use the figure, okay, even though you're just making some assumptions on that figure. Okay, so, and of course, if the compound is something like, for example, this is sulfuric acid, and we know that this sulfuric acid is not actually an inorganic salt, because that's actually that's not a salt, that's an acid, something like that. Now this is also limited to concentrated solutions of inorganic salts. So if you have, let's say for example, this craft liquid or citric acid and glycerol, they're not inorganic liquids. They are not inorganic salts. They're actually organic compounds. So you must be using this figure, okay? But for such cases where you have something like inorganic salts, then you're free to use this Miranda and further correlation. And by the way, this correlation was actually obtained from an experiment they did. That's why it's called a correlation. Anyway, so that's all for this boiling point rise. I hope you've understood how this figure and this BPR works using the equation or the correlation and then using the graph. Okay, so with that, let's end it on the problem wherein we'll be utilizing the boiling point rise. Again, I would also like to emphasize that this boiling point rise is the effect of the concentration of ionic compounds that are dissolved in water. You start with the vapor chest, add the boiling point rise, and then that's the solution of the temperature. And the steam temperature is actually much higher than this solution temperature. And by the way, I was also able to tell you something about this Q, which is equal to UA delta T, wherein this delta T is equal to TS minus TV before, because this is actually for the first effect without any boiling point rise. But if there's a boiling point rise, as you can see here, that's the vapor chest temperature, but the solution temperature is quite the larger one, so this will be replaced with TL, or simply that is temperature of the vapor plus the BPR. Okay, so that will be replaced by that. So anyway, we'll be solving for that, so let's head on to such kind of problem.